When we apply forces on structures, they tend to undergo displacement and deformations. Depending on the nature of the load and the system itself, these changes in displacements may either be gradual or they may happen rather quickly. When a structure undergoes a rapid displacement, even when the load increment is gradual, that state of the structure is nothing but a structural instability. For instance, let's consider these two scenarios where a cylinder is resting on a convex and a concave surface. The stability of this system is defined as a state where the cylinder will get back to its original state when it is subjected to a small disturbance. In the first case, if we give the cylinder a small nudge, it will oscillate about its original position for some time and eventually come back to rest in its original position. So, this is a stable state. In the second case, if we give the cylinder a small nudge, it will roll over the surface and falls and never return to its original state. So this is an unstable state. Every mechanical structure responds to external loads with a reaction force. So each structure has a force displacement response that characterizes its structural properties. If we plot the force displacement response of a structure, we can see if and when exactly the structure becomes unstable. For instance, looking at this plot, we can see that the structure deforms steadily up to point A. Once it reaches point B, any further loading will result in a rapid change in displacement. So, point B is the stability limit of this structure, and loading it beyond this point makes it unstable. At this stage, the structure loses its stiffness and either partially or fully loses the ability to support loads. Structural instabilities occur in many forms, and it's hard to classify them. But we'll try to classify them into two types in our discussion for better understanding. The two types of instabilities are dynamic instabilities and buckling instabilities. This classification is inspired from the terms and governing equations that are responsible for the said instability. But before we dive into the details of each type, let's take a moment to understand why we even need to study the instabilities of structures. Designs for every major construction, such as bridges and buildings, must be assessed for their instabilities to avoid design failure. A famous case for one such design failures is the Tacoma Narrows Bridge in Washington state that collapsed a few days after it was constructed in 1940. It's believed that the wind loads had excited two different modes of the bridge, and as a result, it started swaying dangerously and ultimately collapsed. Fortunately, this incident did not result in any human casualties. But it did serve as a wake-up call in studying the vibrational characteristics of all suspension bridges before constructing them. It's also very important to understand the stability aspects of other engineering structures, such as cranes, load columns, and pressure vessels. This allows the designers in assessing the limiting loads that these structures can be subjected to. For instance, studying the stability limits of cranes will help us in understanding what is the maximum load that can be handled by them. This information is crucial in avoiding many mishaps. It's important to note that this is referred to as structural failure and not material failure. The structure may fail even when the stresses developed in it are well below the material failure point. This may be due to the geometry of the structure. But instabilities are not always life-threatening situations, and in some cases, they are not considered bad news either. For instance, a simple snap-fit mechanism that's commonly used in most electronics enclosures experiences instability at the point of engagement due to a sudden loss of contact. If you have played Jenga, you'll realize that it's played by strategically introducing instability in the structure, so your opponent would tumble it down while moving blocks in their move. Even the act of us leaning carefully over the edge of a cliff is our instinct of maintaining a stable foot. The idea in this case is to keep our center of gravity as low as possible, which improves our stability. So, to summarize this discussion, it's important to understand what makes a structure unstable to ensure both stability and to occasionally use it to our advantage. In this section, we'll learn the different aspects of structural stability and look at some practical applications of stability analysis of engineering designs and structures.